want to dig in to what we can learn by applying big data tools specifically to scientific and research information. Looking at some of the real world applications and how those can practically benefit various stakeholders in the research space. I'll do this through the lens of my experience at Meta, which is a team of data engineers and bench scientists who are focused on a mission that is at once very, very simple and also very, very ambitious. Our aim is to unlock all of the world's scientific and technical insights using artificial intelligence. As of January of this year, Meta is part, as I said, of the Chan-Zuckerberg Initiative, which is the not-for-profit operation founded by Facebook CEO Mark Zuckerberg and his wife, Dr. Priscilla Chan. And CZI also has a very ambitious goal, which is to cure, prevent, or manage all diseases by the end of the century. And as I'll explain over the next few minutes, Meta helps the initiative get closer to this target by providing scientists with the means to make sense of the vast amount of research that's being produced around the world. I'm going to largely take this slide as read because I think you know the essence of what is distilled here. The bottom line is that there are many more articles being published every day than a researcher can possibly keep track of. And given that volume of papers, as well as the complexity, the density of those papers, meaningful engagement increasingly requires new classes of products and services, AI-enabled systems that are able to read and understand scholarly literature at scale. And that's not an easy task, considering that we're dealing with information that is very, very dense, very, very information, documents that are very information rich. So in this case, when we use the term big data, it doesn't just mean volume, although that's part of it. It also means complexity of the data. So Meta was created to machine read, understand, and create structured connections across all of this scientific knowledge. And that opens the door to some very specific use cases, three of which I'll talk about momentarily. One of the really neat parts about being associated with the Chan-Zuckerberg Initiative is that the tools that I'm discussing today, as well as what comes next, are free. So we're releasing these into the wild, if you will, with the hope that lots of different types of researchers, organizations, publishers, and so forth can build upon the tools and can help accelerate the pace of science. I'll also mention that the tools that I'm talking about today are real world applications. They're not abstractions. They're tools that are out there in the ether today. What drives all this, these tools, these AI-driven services, is content that we are machine reading that we've attained from a variety of sources. So we have direct indexing partnerships with hundreds of the world's leading publishers, and more added all the time. And what we do with that is we use that information. We don't serve the full text to anyone, to any end user or any organization, but we use the information to generate a very, very large scientific knowledge graph. So we identify, we map, and we rank the connections between more than 37 million different scientific entities, essentially mapping the entirety of science, both today and also how we got to today. And this knowledge graph becomes the base data set that powers all of these big data applications that I'm alluding to. The first of these is MetaScience, which is a free AI-enabled literature discovery engine. So MetaScience has over 65 million web pages, each dedicated to a specific concept or person that is mentioned in the scholarly literature. And to navigate these pages, there are specialized focus feeds that act as what we call personalized research timelines. From a UX perspective, they're almost like Twitter feeds where new papers, new information populates in a stream on a user's page. And our goal is to present research discoveries tailored to your personal interests in as close to real time as possible, with as few false positives and false negatives as possible. And that's done by machine reading every paper to which we have indexing rights, which is north of 50 million at this moment, and comparing those papers across the 200 plus classes of entities that we extract and normalize from that corpus. And what that allows us to do, in effect, is to compare every new paper across multiple dimensions to every published paper dating back to 1665. And we believe that this discovery path is superior to kludgy saved searches, email tables of contents, RSS feeds, and other methods that researchers typically string together today to try and stay abreast of what's happening in their fields. A second application that I want to quickly highlight is bibliometric intelligence, which helps journal editors manage the flow of manuscripts that they're tasked with evaluating. And we basically look at every submitted manuscript and compare it to every paper that has previously been published, as well as every other paper that's being published today or in recent days on similar topics. And what that allows us to do is it allows us to complement the qualitative editorial expertise that typically goes into evaluating manuscripts. In a nutshell, what bibliometric intelligence does is it helps editors quickly answer 3 core questions for each manuscript they receive. Is my journal an appropriate venue for this manuscript? So we give a journal matching score for each manuscript. What is the potential impact of this paper? So we estimate a 3-year eigenfactor and citation count for each manuscript. And also, to whom should I send this paper out for review? So we identify prospective reviewers for the papers as well. And again, it's not a theoretical service. This has been tested against millions of actual articles. And these tests look at how our algorithms performed compared to actual article level eigenfactor scores and actual citation counts. And we learn from that, obviously. So we test on a set, we recalibrate the algorithms, and then we test again, and then we recalibrate. And that's how machine learning works, right? So it gets better as it goes along. Finally, I just want to talk very, very briefly about horizon scanning, which emerged from a 5-year US National Intelligence Research Program. This is a predictive intelligence engine that looks to make sense of emerging topics and disciplinary intersections and the next what's hot areas of science. And the system works by scanning not just the knowledge graph, but ancillary data sources like patent literature, to identify every entity that gets mentioned everywhere. And then those concepts are analyzed based on a number of semantic patterns within the article sets. And based on those features, the system measures the current global prominence and predicts their future prominence 3 years from now. And so that can help. Imagine, applying this to the problem space of identifying early emergences in drug discovery, drug therapy, translational medicine, locating gaps in existing treatment lines, et cetera, and so forth. And this horizon scanning, again, is being used by organizations presently, and we're in the process of incorporating an end-user facing version directly into the meta.science experience as well. Just by way of summary, I want to reiterate 3 points. One is that the scale of scholarly literature is incredibly large and complex. 2 is that compiling, structuring, and mining this corpus is a substantial undertaking. And 3 is the reward for doing so is tools that can and do provide real benefits to individual scientists, to publishers, to editors, to research and development organizations, all of whom are working to improve understanding of the world's biggest challenges and opportunities. So I have this graphic on the slide because I think it provides a good metaphor for big data analytics. To date, our research developments, our understanding of research developments is much like the visible light spectrum, but there's so much that's going on that we're unable to discern. So what big data tools can do is extend our field of vision, and organizations like Meta, like the other ones you've heard today, are providing the tools that help process those signals.